Imagine a universe that has just been born. Chaos. Plasma boiling at temperatures of billions of degrees. Space itself expanding faster than the speed of light. And in this primordial cauldron, fractions of a second after the Big Bang, something extraordinary is born: black holes. Not from dying stars. Not from neutron star mergers, no. These black holes emerge from nothing, from pure fluctuations in density, as if the very fabric of reality suddenly collapses into points of infinite density. They are tiny, some no larger than an atom, yet they carry the mass of a mountain, or even a planet. They emit no light. They are invisible, and they could be everywhere around us right now. They might be the very dark matter that makes up 85% of all matter in the universe, the unseen substance that forces galaxies to rotate faster than they should. But what if everything we thought about dark matter, exotic particles, WIMPs, axions, is wrong? What if dark matter isn't made of new particles at all, but of ancient black holes, born in the very first moments of the cosmos? Imagine this. These primordial black holes could explain not only dark matter, but also the mysterious black hole mergers detected by LIGO, and even the supermassive monsters at the centers of galaxies that the James Webb Space Telescope is seeing far too early in cosmic history. But there's a problem. If they're too small, they should evaporate, radiating energy through Hawking radiation and exploding like tiny bombs. We don't see these explosions. Or do we? And if they are massive enough to survive until today, then they are perfect candidates for the invisible mass holding the universe together. Today, we're going on a journey through evidence that challenges everything we think we know about the origin of the universe, about dark matter, and about black holes themselves. We'll dive into the chaos of the early cosmos, unpack quantum fluctuations, gravitational waves, and observations from the most powerful telescopes ever built. Get ready. This is a journey from simple ideas to terrifyingly grand conclusions, where reality may be far stranger than we ever imagined. Let's begin. It all started in the 1970s. The great physicist Stephen Hawking was thinking deeply about black holes, those cosmic monsters that swallow everything, even light. But in 1971, even before his famous work on black hole radiation, another scientist, Yakov Zeldovic, and independently Bernard Carr, and Stephen Hawking in 1974, noticed something strange in theoretical calculations of the early universe. In the first moments after the Big Bang, matter density was unimaginably high, and fluctuations, random variations in density, could be enormous. If, in some tiny region, the density exceeded a critical threshold, gravity would win, and that region would collapse into a black hole. There was no need to wait billions of years for a star to explode as a supernova. These black holes, primordial black holes, were born directly from the chaos of cosmic inflation. To understand this, imagine the early universe as a boiling ocean. The waves are density fluctuations caused by quantum effects during inflation, when space itself was expanding exponentially. Most waves smooth out, but the highest peaks, regions of extreme overdensity, do not. If a peak is steep enough, it doesn't disperse. It collapses under its own gravity. The mass of such a black hole is roughly equal to the mass contained within the cosmic horizon at the moment it forms, ranging from the mass of an asteroid to the mass of 1,000 suns, depending on when it forms. The earlier it forms, the smaller its mass. The fundamental principle here is gravitational collapse in an expanding universe. In today's universe, forming a black hole requires an enormous amount of mass squeezed into a tiny volume, like the core of a massive star. But in the early cosmos, the particle horizon, the distance over which things can be causally connected, was incredibly small. Anything within that horizon that exceeded the critical density would collapse. Here's a simple analogy. Imagine an inflating balloon. If you draw a dot on the surface and then pinch that spot harder than the rest, that point can cave inward, forming a separate structure. Primordial black holes cave in from the expanding fabric of space itself. The central mystery appeared immediately. If these black holes exist, Where are they? Small ones should have evaporated through Hawking radiation, a quantum effect where particle-antiparticle pairs form near the event horizon. One falls in, the other escapes, carrying away energy. The black hole glows and loses mass. For a black hole with the mass of a mountain, about 10 superscript 1 superscript 2 kilograms, the lifetime is roughly the age of the universe. Smaller ones would have exploded long ago. Larger ones would survive indefinitely and could be dark matter. At first, the scientific community was skeptical. In the 1970s, dark matter itself was only beginning to reveal its presence. Fritz Zwicky had noticed strange galaxy motions back in the 1930s. Vera Rubin confirmed flat galaxy rotation curves in the 1970s. But the explanations focused on modified gravity or invisible particles. The idea that dark matter might be black holes from the Big Bang seemed far too radical. In 1974, Hawking calculated that if primordial black holes made up dark matter, the smaller ones should be exploding today, producing gamma-ray bursts. But telescopes like Fermi didn't observe them in the expected numbers. Then came decades of constraints. Microlensing, when a black hole passes in front of a star and amplifies its light through gravitational lensing. Surveys like MACHO and OGLE detected some events, but not enough to account for all dark matter. Massive black holes were constrained by the dynamics of galaxies and clusters. Very small ones were constrained by the absence of evaporation explosions. And yet, the data began pushing us toward an uncomfortable conclusion. The standard dark matter candidates, WIMPs, have not been found. The Large Hadron Collider saw no supersymmetry. Underground detectors like Xenon detected nothing. Axions continue to evade us. Meanwhile, in 2015, LIGO detected mergers of black holes with masses of 30 to 50 suns, uncomfortably heavy for normal stellar evolution. Some events fell into forbidden mass. And in the 2020s, James Webb began seeing supermassive black holes in galaxies less than 1 billion years old, far too early to have grown from ordinary stellar black hole seeds. The unsettling thought emerges. What if part, or even all, of dark matter is made of primordial black holes? They would naturally form binary systems in the early universe. They would merge, producing gravitational waves. They would seed early galaxies. And if their mass distribution is just right, from asteroid mass to solar mass, they could hide perfectly in plain sight. And this is only the beginning. Next, we'll see how the evidence continues to accumulate, challenging the standard model of cosmology. How LIGO may be seeing clues hidden in black hole mass distributions. How JWST is uncovering impossible early monsters. And how future missions could finally confirm or destroy this radical idea. The universe may be hiding its darkest secret in the oldest objects of all. Now we dive deeper. Imagine the fabric of space-time itself, trembling from distant cataclysms. In 2015, the LIGO detectors in Louisiana and Washington recorded something once thought impossible: gravitational waves from the merger of two black holes with masses of about 30 and 36 times the mass of the Sun. This was the first direct proof that black holes truly exist. But here is what shocked scientists. These masses, 30 to 50 solar masses, fall into the so-called forbidden zone for ordinary stellar black holes. For a star to leave behind a black hole that massive after a supernova, it must be extremely heavy. Yet in exactly this mass range, physical processes such as pair instability supernovae completely tear the star apart, leaving no black hole at all. The classical explanation, mergers inside dense star clusters or hierarchical mergers, can work, but only with fine-tuned, highly specific conditions. But what if these black holes didn't come from stars at all? What if they are primordial black holes, born directly from the chaos of the Big Bang? Within the LIGO, Virgo, CAGRA observatory network, scientists have now detected dozens of such events. By 2025, during the fourth observing run, 04, The collaboration recorded mergers with component masses ranging from subsolar values all the way up to hundreds of solar masses. The most intriguing events are those where the components lie between 20 and 50 solar masses. For example, in November 2025, LIGO/Virgo/Cagra reported an unusual signal from a merger whose inferred masses suggested a subsolar population, a potential hint of low-mass primordial black holes. The concrete parameters are staggering. The distance to the event, billions of light-years. The energy released in gravitational waves, equivalent to several solar masses converted entirely into pure energy in a fraction of a second. For scale, a single such signal carries as much energy as the simultaneous explosion of tens of billions of suns. The classical explanation, astrophysical black holes form from the first generation of stars, known as population 3 stars, breaks down for several reasons. These first stars were indeed massive, but models show that they tend to explode in ways that leave behind black holes either lighter than 10 solar masses or heavier than 50. To produce a peak at 30 to 40 solar masses, very special conditions are required: extremely low metallicity, finely tuned rotation rates, and specific evolutionary paths. Yet the mass distribution observed by LIGO shows a peak exactly where primordial black holes are expected, especially those forming from density fluctuations during the QCD epoch, less than 10 seconds after the Big Bang. The characteristic mass of such PBHs is around 1 solar mass, with a broad distribution extending upward. Why does the classical picture fail? Because for astrophysical black holes, binary systems form slowly in the early universe. You need time for stars to evolve, explode, and then gradually spiral together. But LIGO observes mergers at redshifts z greater than 1, when the universe was less than a few billion years old. For primordial black holes, binaries form naturally. In the dense environment of the early universe, PBHs gravitationally capture one another long before stars even exist. Simulations from 2024 to 2025 show that if primordial black holes make up even 1% of dark matter, they produce exactly the merger rate and mass distribution observed by LIGO. But this is only a small piece of a far stranger picture. Now we turn to the telescope that completely reshaped our understanding of the early universe, the James Webb Space Telescope. Between 2022 and 2025, JWST discovered galaxies at redshifts z greater than 10, when the universe was less than 500 million years old. These galaxies are bright, massive, up to 10^1 solar masses in stars, and at their centers sit supermassive black holes with masses ranging from millions to billions of solar masses. In 2024 to 2025, spectroscopy confirmed black holes in the so-called little red dots, compact objects at z is almost equal to 8 to 14, hosting black holes with masses of 10 suns, embedded in galaxies whose stellar mass is barely sufficient to support such growth. One striking example is Able 2744, QSO1, identified in 2025. Its black hole appears to exceed even the dynamical mass of its host halo. The distance, billions of light-years. The temperature of the accretion disk, millions of degrees. The radiation output, X-ray and ultraviolet emission equivalent to billions of suns. The scale is breathtaking. This black hole grew to 1 billion solar masses in a time when ordinary seeds, stellar black holes of 10 to 100 solar masses, simply cannot grow fast enough, even under super-Eddington accretion. The classical solution, direct collapse black holes formed from massive gas clouds of 10 solar masses, works only partially. It requires nearly perfect conditions, no fragmentation, extremely efficient gas inflow, and fine-tuned environments. Why does this explanation fail? Because JWST sees far too many such objects, up to 2 orders of magnitude more than lambda CDM models predicted before 2022. And many of them are overmassive. The black hole dominates the stellar mass of the galaxy, sometimes by 30 to 100%. Now comes the most shocking development: the possible role of primordial black holes as seeds. Studies from 2024 to 2025, including simulations with PBHs of 100 to 1,000 solar masses, show that these seeds dramatically accelerate growth. They seed halos earlier, accrete gas more efficiently, and even a tiny fraction of PBHs, 0.1 to 1% of dark matter, can explain the excess of bright galaxies and massive black holes at Z greater than 10. More than that, in 2025, researchers proposed that PBHs with QCD scale features, or those forming in clusters, could naturally create exactly these impossible systems. All of this evidence points beyond standard particle cosmology and toward a radical hypothesis: dark matter, or a significant fraction of it, is not made of WIMPs or axions, but of relic black holes from inflation. LIGO gives us the echoes of their mergers today. JWST reveals their impact on the first galaxies yesterday. But the picture grows even more paradoxical. Over the past 5 to 10 years, data have accumulated from microlensing, orbital anomalies in the solar system, and even the thermal evolution of the intergalactic medium. In 2025, a study from UC Santa Cruz suggested that asteroid-mass primordial black holes may pass through the solar system once per decade, inducing a subtle wobble in Mars' orbit, a deviation future missions could measure. The parameters: mass 10 superscript 1, 10 superscript 2 superscript 2 grams. Velocity 200 km/s. Effect: millimeters of orbital displacement over decades. Particle dark matter cannot explain such localized gravitational disturbances. For primordial black holes, this behavior is natural. If they populate the Milky Way halo as dark matter, a density of 10 superscript 1 superscript 2, 10 superscript 1 kg per cubic parsec, leads to rare but inevitable close flybys. Another clue: in 2025, new constraints from the temperature of the intergalactic medium, derived from the Lyman alpha forest, showed that light PBHs evaporating via Hawking radiation heat the gas less than previously expected, reopening a window for masses around 10 superscript 1, 10 superscript 1 grams. Heavier masses face strong constraints, except for the asteroid mass window. Putting everything together, the unusual spins and masses seen by LIGO, 2024 to 2025. The early supermassive black holes revealed by JWST. Possible solar system flybys. And the complete absence of particle dark matter signals at LHC and xenon. All converge on a single hypothesis. Primordial black holes not only exist, they shape the universe from microscopic to cosmic scales. The most shocking implication: if primordial black holes are dark matter, then billions of them surround us, right now in the galactic halo, invisible, yet gravitationally active. They may be passing straight through Earth at this very moment, interacting with nothing except gravity. And future detectors, LISA, the Einstein telescope, may detect their echoes in the millihertz gravitational wave band. But this takes us even further, toward a grand picture in which primordial black holes explain not only dark matter, but the origin of supermassive monsters, and perhaps even inflation itself. We are approaching a theory that rewrites everything.